It gives me great pleasure to introduce my friend and research colleague, Erik Demaine, who is a professor in the Department of Computer Science, or the Laboratory of Computer Science and Artificial Intelligence at the Massachusetts Institute of Technology. Unlike most of us, Erik Demaine didn't have time to go to grade school, elementary school, or high school, because he was too busy at home being schooled by his father. And also, unlike most of us, he didn't waste any time at home, because in 2 years, at age 12, he went to university and finished his bachelor's degree in 2 years at 14. I met him when he was a young teenage PhD student, and we immediately started collaborating on research problems in computational geometry and discrete geometry, which we are still doing today. And at that time, his plan was to become my postdoctoral student at McGill University. But when MIT offered him a job, he changed his mind and became the youngest professor in the history of MIT. His numerous awards, prestigious awards, started coming early. I'll just mention a few. His dissertation, his PhD thesis, a seminal work on computational origami, which is the topic of today's lecture, won the Canadian Governor-General's Gold Medal, as well as Canada's Natural Sciences and Engineering Doctoral Prize for the best PhD thesis in Canada. In 2003, he was awarded the MacArthur Fellowship, more commonly known as the Genius Grant, and the MacArthur Fellowship citation reads the following: Erik is a computational geometer tackling and solving difficult problems related to folding and bending, moving readily between the theoretical and the playful, with a keen eye to revealing the former in the latter. I could go on much further talking about his other awards, many books and papers, but I will guide you instead to Wikipedia or his webpage so that we have more time for him to unfold his research before our eyes. So please welcome Erik Demaine.
Thanks, it's a pleasure to be here. I'm excited to have some fun folding. You guys excited? All right, gotta wake up a little bit. So I'm here to talk about origami, paper folding, as both an art form and a science. And origami is really exciting in this way that it brings together both art and science. I'm a computer scientist by trade. I guess I'm also an artist. And I really like playing in this world of paper folding because I get to do both at the same time. And I claim that we are better artists because we also study the science. And we're better scientists because we also study the art. And I want to encourage you all to think about things not just from the way you're used to thinking about things, but try collaborating, try working outside your usual limits and fields, and think about the other side. Whether you're an artist or a scientist or neither, or some other field, see what might be interesting there. I work a lot with my father, that's Martin Demaine here. And while my background is in science, his background is in the arts. And over the years, we've known each other a long time. And over the years, we've come together, so we're now both artists and both scientists. And it's really a lot of fun working together, partly because we're family, and it's really cool, and we work really efficiently together, but also because we've got to learn about the other side and see what art is like and see what mathematics is like. So that's where we're going. I'm going to start with a kind of an art talk. Starts with, how did you get here? What's your personal background? And our story begins with the Demaine Glass Studio. This is before I was born, so Martin Demaine Glass Studio in New Brunswick, Canada. My dad was the father of Canadian glass, and he was commissioned to make goblets for the Queen of England and all sorts of cool things. This is in the early glass movement. And then our first collaboration was when I was 6 years old. That's me. I look a little different now. That's my dad. And we made and sold these wire take-apart puzzles across Canada in toy stores. And it was a really fun time and the beginning of my interest in puzzles, and probably also the beginning of my interest in mathematics. and really the beginning of our collaboration and sort of starting to work really closely together as equal partners. We split the money 50-50, and then shortly thereafter, so when I was ages 7 to 11, so about 4 years, we traveled around mostly the East Coast of the United States and lived in all sorts of different places. We lived in about 10 places in those 4 years. And again, as equal partners, we would always decide, I think it's time to move. Okay, where should we go next? And we figure out what would be interesting. Because we were traveling a lot in the beginning, we tried out homeschool, and homeschool worked really well. As Gottfried mentioned, my dad taught me. And that also kind of made us closer and bonded things a lot. And I got to finish school faster and all that. But what was really cool about homeschool is meeting and traveling so much, was meeting lots of different people, all sorts of different backgrounds. Everybody knew something different. And so we got to learn from different people and from people from all different age groups. And this leads today to our very collaborative spirit. On the mathematics side, I've written papers with over 300 people. Gottfried is one of the first. And sort of taught me this way of working collaboratively with people, and it's very powerful in the mathematical side. It's less appreciated on the art side, and one of the things we're trying to do is bring this collaborative spirit to art as well, and sort of taking down the ego of the artist, and just having fun and working with lots of people and making something together that no one person could make. These days we're both at MIT, been there for the last 11 years. This is our building. It's a Frank Gehry building. You're going to get a Frank Gehry building pretty soon, the new Guggenheim. MIT is a great place for doing this kind of thing of combining science with art. There's a lot of science there, a lot of scientists, a lot of scientific tools, and also a lot of people excited about arts and just building crazy things, making sculpture. And a lot of the scientific tools can also be used for making art things. Instead of just serious things like robots, you can also build sculpture with laser cutters and other fun tools. But MIT also has a lot of art studios. It actually has a glass blowing studio. And so when we moved here, I got to see for the first time my dad blow glass. And then we started blowing glass together, and I learned how it worked. These are a couple of examples of pieces that we made together. These are kind of designed to be puzzles for glass blowers to figure out how they're made. And it's a little hard to see on this screen, but these are glass vessels. It's hollow in the center. Then there's like this tentacle that comes up from the bottom and connects to the sides. And it's a little tricky to reverse engineer how this is made. You can eventually figure it out. You can ask me after if you want to know. But it's a fun challenge to figure out how do you get that color in the middle and how do you get all those connections. A couple more examples in that series. This is some of our first work together in the glass side. But this is a talk about folding. And what does glass have to do with folding? Well, it turns out you can fold glass too. This is one of our latest explorations just over the last year with Peter Hauk, who runs the glass lab at MIT, and Amy Nichols, who is a student at MIT. We've been experimenting with lots of different ways to fold glass. Glass folds very differently from paper, but it's cool in the ways that it's different. It's very hard to fold physically because it's around 2,000 degrees Fahrenheit when it's most flexible. So it's like the temperature of an erupting volcano. You can't just touch it. But with the appropriate tools, you can do a lot of things. This top example here is one that we made essentially without touching it. We first laid out strips of these of the yellow glass, which is fairly stiff, and then put on these little black connectors. Just put them on top of each other, and then bring everything up to temperature, and it fuses it all together. The black glass becomes very flexible relatively quickly, so it acts as a hinge. And then you put this in an annealer in an oven, you heat it up even more, and then it starts folding. If you take it out before it completely folds, you get these nice partially folded structures where the yellow is relatively unfolded and the black is more folded. These examples are based on a somewhat more hands-on technique, which is illustrated here. This is Peter Hauk. And here we've got hot glass. This kind of acts like honey. It's a little bit slower than honey, a little much more sticky than honey. So it's hot there, and we're laying it over this a bunch of angle iron, 90-degree angle iron, and then squishing it into the crevices there. And then you get a nice zigzag pattern. So you folded your glass, and then you can put on these Kevlar gloves and start folding it into some shape. This is how this goblet was made. And the goblet, the top is a separate piece, but then you get a neat mix of folding and glass. And it's been a lot of fun for us to this is very different from traditional glass blowing, and it's neat to play with. But the rest of the talk will be about paper folding. So paper folding goes back at least 300 years, possibly thousands of years. This is one early book on paper folding, and it's actually fairly advanced for its time. It's folding not just one origami crane, but folding 3 origami cranes simultaneously from one rectangle of paper. So this rectangle has 2 slits cut in it. At the time, cutting slits in paper was considered legit. And you fold each of these squares into an origami crane. If you're very careful, you won't tear the corners. And then the cranes will be connected in the end. And you can make very complicated arrangements of cranes in this way, hundreds of cranes all in out of one sheet of material. These days, the modern origami art form transformed a lot in the last 30 years or so. And these days, extremely complicated forms are made from one square of paper with no cuts. It's like the extreme, difficult origami. And yet you can make a 3-headed Cerberus or a dragon with about 1,000 scales on it. These are 2 designs by Satoshi Kamiya, one of the leading young Japanese designers. And they're just incredibly complicated and detailed and beautiful. The dragon, I'm told, took about a year to fold. And it's not easy. And so how are artists able to achieve such difficult forms? The claim is through mathematics and science. That's where we'll be getting to. Here are some more examples of complex origami design. This was a design challenge to fold a sailboat. And you could, on the upper left here, take a square of paper that's brown on one side and white on the other. And you can fold the sails a different color from the boat. People have 2 different colors. You could fold a kind of bas-relief sailboat. You could fold a sailboat with the sails closed. This is technically very challenging. Doesn't even look like it, but it's one square of paper. Or you could fold a sailboat with the sails open. This is, again, a color reversal. It's white, paper is white on one side and green on the other. Or you could fold a sailboat being cracked into 2 pieces by a giant kraken, all from one square of paper. The water is a different sheet of paper, but the 2 pieces of the boat and the squid are one piece. Top 3 designs are by MIT students, so I'm proud of them. I was visiting the Grand Mosque yesterday. Wow, is that only yesterday? And it's very cool and beautiful, amazing, intricate design. And it reminded me of this field of origami tessellations, which is taking those kinds of designs and translating them into foldings. Each of these is one square folded just kind of a little bit to make little pleats, and the pleats make these shadows, darker shadows when you hold it up to the light. So here there's only 1 layer of material, here there's 3 layers of material, and here there's even more. That's what makes the darkness happen. So you could translate a lot of the designs in the Grand Mosque to paper folding as well. I just mentioned that that's out there. I won't be talking much about origami tessellations here, but there's interesting mathematics as well. That idea of origami tessellations is growing to capture more 3-dimensional structures, like this mask by Joel Cooper, one of the best tessellation folders out there. And origami every year makes more and more, artists make more and more exciting and beautiful designs, very lifelike and representative, some more abstract and geometric. I'll be talking more about abstract and geometric forms because that's sort of our world. But first I want to tell you about what is the mathematics that underlies a lot of these designs. When you go to fold an origami butterfly, most people don't just sit down, pick up a square, and try to fold it into a butterfly shape. They plan. They think about which parts of the paper, like this region here, are going to be used for which parts of the model. And they reserve different parts of the paper So there's just enough material wherever you need it in that design. And there's a mathematical understanding of how to go back and forth between these. And every complex origami designer knows that correspondence and can design these kinds of layouts to get paper in roughly the right locations. And then there's the sculpting part of making it actually look like a butterfly. So the mathematics underlying that theory is called the tree method of origami design. And it was developed by many Japanese origami designers and Robert Lang in the US. And the three of us have been working together over the last several years proving that this method always works mathematically. And the idea is the following. Suppose I want to fold something like a lizard. Well, first I'll draw a stick figure of the lizard. It's got a head, it's got 2 forelegs, a body, and then some hind legs and a tail. Let's say a simple example. I'd like to fold a piece of paper that has roughly that structure. It has some material for the head, it has some material for the foreleg. And I'm going to represent that by the stick figure. And I even get to control how long each of these segments are. I can make the head really long relative to the legs or whatever. And then what this algorithm gives you, this computational procedure, will tell you the best way to fold a square piece of paper into some origami whose projection is exactly that stick figure. That's what's drawn here. If you don't know projection, don't worry. This just means there's a portion of the paper, it's called a flap, that's kind of independently manipulatable from all the other flaps. And there's one flap per segment over here, and they're connected together in exactly the right way. So it gives you this assignment of which parts of the paper are used for which parts of the model. And on the top, there's a more complicated example. Suppose you want to fold a scorpion. This is a design by Robert Lang. If you take this stick figure as your representation of a scorpion, it's got the pinchers, enough legs, some extra material here, and a big tail. You put that into this tree method of origami design. There's a computer program here called TreeMaker that will give you this crease pattern. And when you fold it, you get this thing called an origami base. It has exactly one flap. It's hard to see because there's lots of flaps on top of each other, but there's exactly one flap for each of these segments. And then you just do a little bit of shape folding, and you get your scorpion. Easy. So this method captures a big part of origami design, which is how do you get all the flaps in the right places. But it does not capture this artistic step, the shaping step. And if you're an experienced origamist, this is not too hard. But as a mathematician, it's kind of unsatisfying. I'd like to understand the mathematics of everything. I want to know, how do you get all the way to the scorpion? And so we have a new technique, so we started wondering, what shapes can you fold? If I have a big enough square, can I fold any two-dimensional shape, any polygon? Can I fold any two-color pattern? If I have a square that's white on one side, black on the other, say, can I fold a zebra? Or more generally, can I fold any three-dimensional surface from one square of paper? So this is beyond just stick figures. And it turns out the answer is yes to all of these questions. You take a large enough square of paper, you can fold any shape as long as it's made out of flat sides. So these have to be straight segments here. And this is actually an old result. It's one of the first things that we proved back in '99. But until recently, we didn't know an efficient way to fold these shapes. We'd start with a piece of paper the size of the moon and fold a microscopic horse with stripes on it with our old method. Our new method is called Origamizer, and this is also free software you can try online. This is originally by Tomohiro Tachi, and then again, the two of us have been working on proving that this works always. And so you start with an arbitrary 3D model that you've been designing on your computer, or you could scan a clay model or whatever you want. You give that to the software. It gives you a crease pattern. The solid lines here are mountain folds. The dashed lines are valley folds. You fold this from a square of paper. It contains this shape. It takes about 10 hours if you're good, and you end up with this folding of this rabbit. So it's definitely challenging. There's no way this would ever be designed by a human, but with the computer helping you out, you can come up with extremely complicated crease patterns that fold into exactly what you ask for, which is pretty exciting. And you can apply this technique not just to fold sheets of paper, but to fold other sheets of material. So for example, Tomohiro was visiting MIT last year, and we laser cut a sheet of steel. This is Tomohiro in real time. He's really that fast. And this is a period of about 10 hours. And so we laser cut this sheet of steel. We cut out some holes to make it a little easier to fold because this material is quite a bit thicker. And we perforated the crease lines. And you see the sun just went down. And keep folding, folding, folding with gloves, because otherwise you cut yourself. And eventually you get a steel origami bunny from one sheet of material. Pretty cool. So it's really exciting. From one sheet of material, I mean, you can buy almost any material in sheets. Now you can fold any 3D shape out of that 2D sheet. I wanted to show you another fun problem, and I could use a volunteer, perhaps. Anyone wants to come up? Don't all jump up at once. I'll cut the first one, but then I want to make sure, I want to prove that I'm not cheating. So think about whether you want to volunteer. We have here a rectangle of paper. Fold it here. Rectangle, I fold it flat, and I make one complete straight cut. The question is, what shapes can you get by folding and one complete straight cut? In this case, I get 6 pieces. 5 of them are, I think I practiced this. 5 of them are isosceles triangles. Whoa. Somehow that never impresses people. Then the 6th piece is everything except those 5 isosceles triangles. Okay, slightly more impressive, but it's a tough audience. So can I have a volunteer? Yeah, all right. Come on up. Now, we've never met before? Okay, good. What's your name?
Serene.
Serene. All right. Now, Serene, I'd like you to, I've pre-folded a piece of paper here. Just cut along that line.
That one there.
Yes. Cut straight. And faster. No pressure. We've still got an hour. Oh, don't cut me.
Like that, yeah.
Yes, exactly. All right, you want to unfold that? I shouldn't touch. Just the one piece. You can throw that one on the floor. We'd make a mess. I'll get the next one. Keep unfolding. Hold it up. Sideways, like this. It's an angelfish. All right, next one. Put you to work here. Cut. Oh, not that line. Just kidding, just kidding. Keep cutting. It's got to stress you out here, Serene.
Yeah.
All right, let's see how we doing. Yes, yes, hold it up that way, perfect. It's a butterfly. Let's see that. All right, yay. It doesn't fly, unfortunately. We have one more. This is the grand finale, so do a flourish or something. Hold on to this piece. All right, we have a little swan. Yay! Thanks, Serene. Yes. All right, let's make a mess. So as you might guess here, there's a general mathematical result that you can make any shape you want by folding in one straight cut. This is actually an old problem. It goes back to Harry Houdini. Before he was an escape artist in the 20s, he was a general magician, and he did all sorts of tricks. One of them, which I assume he performed, is in this book that he didn't actually write. It was probably ghost-written, but I assume he still performed this trick, where you take a square of paper, fold, and make one straight cut, and you get a regular 5-pointed star. Pretty cool. But the problem is actually much older, from 1721. This is one of the earliest books we know of that talks about paper folding. It's a Japanese puzzle book. And this is the question page, and this is the answer page. and it's asking, can you make this Japanese emblem shape from a piece of paper by folding in one straight cut? And you can. And so this was our motivation. We were curious. I was just starting out as a grad student, wondering, well, let's try to solve this in general. Can we do any shape? And to our surprise, we could. This is an example of one of the crease patterns. When you fold it up and you cut along this line, you get that swan that I showed you. And so we were motivated by basically magic tricks. We wanted to design more general, cooler magic tricks to impress our kids or whatever, our kid friends. I don't have any kids, but I guess impress me, my dad's kids, whatever. And so we were trying to solve that. And just as a fun mathematical problem, it turns out it has useful applications as well. It relates to airbag folding. So when you have a three-dimensional airbag, which is like essentially a piece of paper, you want to fold it flat for storage in your steering wheel. You want to fold it flat in a nice way that uniformly distributes the pressure. So when you expand the airbag, it doesn't just put all of the pressure into your face. It kind of distributes it to the sides. And there's this company that uses computational origami, and specifically this fold in one cut stuff and the tree method of origami design to fold airbags safer, better. So origami saves lives is the tagline I saw in the media. So pretty cool and exciting and totally unexpected. You never know. It turns out folding has lots of practical applications. I'm talking here mostly about the sculpture side, but here's a little bit about the engineering and science side of it. The next example I want to talk about is called pleated folding. And this is the topic we've been exploring, my dad and I, for 13 years, I guess. And over the years, we've gone back and forth between art and math and 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 art. And I wanted to give you a little tour of what that alternation has been like and how the art side has inspired the science side and vice versa. We start with this example. I just have a small one here, but it's the same as what you see up there. This is a very simple folding. You should all try it at home. You take a square of paper, and you fold concentric squares, alternating mountain, valley, mountain, valley. And when you put all those creases in, the paper pops itself into this cool saddle surface. We call it self-folding origami, because all I did was put in squares, and yet the paper wants to live in this 3D shape. Why? I don't know. Well, that was the question. So this design actually goes back to the Bauhaus in the late 1920s. You can see one up here. There's this guy, Joseph Albers, and his students either invented or he invented it. I'm not sure exactly. Also see some early tessellations. So they did some of the very first geometric origami designs. And so we knew this model became quite traditional in the origami world, I think in the 80s or so, became popular. And so we thought, oh, let's do something with it. The first thing we tried to do is build sculpture. What if we took many hyperbolic paraboloids and joined them together? And to help us do that, we came up with a computer algorithm that told us if we wanted to represent some 3D shape like a cube, it's called a polyhedron, then the algorithm would tell us, here's a way to join together, in this case, 24 hyperbolic paraboloids together. Maybe I didn't mention this thing is called a hyperbolic paraboloid. So if we could join them together to represent that cube, and then I take another shape, and that gives me a different way to join together, in this case, 12 hyperbolic paraboloids. In general, it's twice the number of edges on the surface. That would sort of give us a way to generate sculpture mathematically, and then we build them physically. In principle, this is an infinite series of sculptures. We've only made finitely many of them so far, but can keep going. So that was on the sculpture side, using mathematics as a tool. You can, even more complicated, instead of just folding concentric squares, you can fold concentric circles. Here you have to cut out a circular hole from the piece of paper. This is not to scale, obviously, but just to give you an idea what the crease pattern looks like. You just alternate mountain, valley, mountain, valley. You could fold those circles, say, with a compass, and you get pretty cool, another 3D saddle surface. This also goes back to the Bauhaus in the late 1920s. Here's what it looks like to fold one in real life. This is my dad's hands. In reality, this takes about an hour or so depending on how complicated the shape is. But once you put those creases in, it just pops into that 3D form all by itself. It's pretty cool. Now, one exciting thing about these self-folding designs, because the paper just wants to live in that 3D shape, in principle, you don't even need an origamist to fold it. You could imagine, and here we've actually built a simple example of a sheet of material where we've cut little grooves on the crease lines and put into those grooves a material. It's this material, if you've ever had a puffy sweatshirt with like letters, puffy letters, it's the same material. This material has the property, initially it's very small. When you heat it up, it grows in volume, kind of crystallizes. And so when you put this thing in an oven and heat all of those creases up at the same time, it folds itself into that 3D shape. So you could imagine on the application side, you want to deploy a space station in orbit or something. So first you take this flat sheet, you bundle it up or whatever, you put it in your space shuttle, you send it out there, you unroll it in space where you've got lots of room, and then you push a button and you actuate, you make all of these creases fold at once, and it pops into whatever 3D form you want. That's the vision, and that's why we're trying to understand this self-folding origami world from the application side. But it turns out to generate really beautiful sculpture as well. So why does this work? We thought, well, let's build a simulator. Let's use mathematics to figure out what's going on. It's also physics here. So the top 3 pictures are real photographs of real pieces of paper, and the bottom 3 are from our software that simulates what's going on. And they look the same, so we were simulating what paper does. Here's an example of what happens with concentric hexagons instead of squares or circles. And essentially what the paper is doing here is wherever you crease it, it wants to stay bent. And wherever you leave the paper uncreased, it wants to stay flat. That's elastic material. And this is the equilibrium that that physics finds for you. The folding happens automatically. Now, once you have a virtual model of a physical folding, natural thing to do is close the loop and make a physical sculpture of the virtual model of the physical piece of paper. So this is that sculpture. It's about 1 meter in diameter, and it's made up of aluminum rods and 3D printed plastic spheres. Each of the spheres has holes at just the right angles as predicted by that simulation, so that when you put the aluminum rods together, those aluminum rods become the crease lines of the paper, and the rest of the paper is kind of erased in this picture. And so it holds it in the static structure that the piece of paper would want to fold into. So it lets you build much larger structures that still represent the folding of paper. So you can see the alternation here. We understood things mathematically, and then we built it sculpturally. So next we go back to mathematics. I've mentioned this hyperbolic paraboloid. At this point, we've folded thousands of them. So it was quite a surprise a few years ago when we discovered it doesn't exist. This thing I'm holding in my hand is mathematically impossible. It's a figment of your imagination. What does it mean? Well, the mathematical statement is if you take a square of paper and you crease on exactly these lines, it cannot fold into anything. So what must be happening in reality is that it's not just creasing on those lines. It must be creasing elsewhere. And we proved that would be enough. Here are some extra crease lines you can add. They're the purple lines. The black lines are the original ones. And when you do that, it folds in exactly one way, and it has a nice parabolic cross-section, and it looks very nice mathematically. It looks pretty similar to what we see in a piece of paper. And so probably what reality is doing is adding lots of little extra creases that kind of approximate that picture. But a fun mathematical surprise is the things we've been building don't exist. So this is the title slide, and in the background here is one of our first sculptures in the world of curved creases. And this is in a permanent collection in the Museum of Modern Art in New York. And it's based on trying to extend this circular concentric circle idea to go a little bit farther. Now, circles go around 360 degrees. We wanted to do more. More is always better. So we decided to go around 720 degrees. It's kind of like a parking ramp. And then, so it's made of two physical pieces of paper, but in principle it's like one sheet. And then you join the ends together, and you pleat that with concentric circles, and the paper twists a lot. Here, it goes here, it runs up to there, and around, and around, and it's cool. And the paper's doing this itself. It wants to fold into the state because of all of that creasing, and because of the elasticity of the material. This is one of actually 3 pieces, and we found that just by changing small parameters of the model, here there's a bigger hole cut out. Here we folded the creases a little less. You really change what 3D shape you get. And the goal is to be able to predict this mathematically and to be able to design automatically. I say, oh, I want a space station that looks like this. How can I unfold that? How can I design a crease pattern that self-folds into that 3D shape? That's the mathematical goal. We're not there yet. We started building these sculptures to basically explore that space and see what was possible mathematically. Towards that end of the more mathematical goal of making any 3D shape you want, we started experimenting with what if you use ellipses? What if you offset those ellipses in different ways? You get a lot more control over your form, get weird asymmetries, and in general, get a better handle on different 3D surfaces. Back on the sculpture side, we started sort of going back to our roots. Initially, the first thing I showed you in the pleated folding was concentric squares and joining many of them together. Well, what happens? Squares don't exist, so we don't want to use these. What if we're folding concentric circles and we combine multiple of them together? So here we've joined 3 concentric circle models together. They kind of, you can squeeze them really tight and weave them through each other. I'll show you that in a moment. And get them to kind of lock together and, again, rest, find this natural equilibrium state where they want to be. And you get some really cool forms. This piece, this is one piece from different views. And these are 2 other pieces. These are in the Renwick Gallery at the Smithsonian in DC. And here we've started experimenting with other papers. We've started gluing together 2 sheets of 2 different colors. So you get a nice color reversal whenever this guy flips over. Here from a light to a dark color. And getting a little bigger. Here's a quick example of what it might look like to put these together. In general, we spend days or weeks to figure out a nice arrangement, but they just kind of squeeze, and if you're lucky, they fit together, and you can get them to make a nice arrangement. And again, in principle, this could be self-folded. You could program multiple sheets here to come together like this. You see some other fun things here. These are sheets of dollar bills, and which you can get from the US Mint. And here's one folded into a concentric circle model. A little hard to see, but one of our crazier ideas. Sculpture worth real money. So that was sculpture. Let's go back to mathematics a little bit. This is a bit of a mathematical puzzle, not super practical, but kind of a fun question. It's really tedious to fold all this pleating. Mountain, valley, it takes forever. It'd be great if we could save some time and just and do most of those folds all at once. Because if you take a piece of paper and fold it in half, and fold it in half, and fold it in half again, you make exponentially many creases. If you make n folds, you make about 2 to the n creases. That's really efficient. That would save a lot of time. The trouble is if you unfold that thing that you made by folding, you do not get mountain, valley, mountain, valley, mountain, valley. You should try it. It will be mountain, 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 valley, mountain, valley, valley, mountain, valley. It's a weird pattern of mountains and valleys. It's called a dragon curve. You can check it out. It's also called the Jurassic Park fractal, because it happened to be in the Jurassic Park book. Anyway, you do not get what we want, which is pleating, mountain, valley, mountain, valley. It turns out you can do almost as good. With n folds, you can make 2 to the square root of n creases. This is a funny number, but believe me, it's really big. So you can still be very efficient and get a perfect alternation mountain, valley, mountain, valley. In theory, in practice, you'd never do this because you get too many layers and you wouldn't be very accurate. But it's kind of a fun math puzzle motivated by the sculpture. And if we weren't making the sculpture, we wouldn't have thought of this problem. Back on the sculpture side, these days we're making bigger sculptures with a lot more pieces. This is on the order of 10 pieces. Experimenting some with leaving some parts of the paper uncreased. This is made from a square of paper, and these are the corners, 2 corners of the square, and some other corners are in there. And we just crease concentric circles and then leave the outer frame uncreased, but it still curves in 3 dimensions. And we've been trying different colors, and this is another really big one. Hoping to go even a little bit bigger. At some point, the paper won't be able to support its own weight, but at this scale, it works really well. And we've been having a lot of fun just exploring this space of sculpture, again, motivated by the mathematical question of what is possible by self-folding. Okay, back on the math side and also the sculpture side, there's this guy, David Huffman, who's very famous in the computer science world. Many of you, I'm sure, have heard of Huffman codes. Every MP3 player, every cell phone, pretty much any digital device you've used uses Huffman codes to compress data to take less space. And so he did that in the 60s when he was a graduate student at MIT. But he also, from the 70s onward, was one of the pioneers of curved crease folding. And these are all his designs, and some really spectacular stuff, and still kind of ahead of his time. He died around 2000, but still many people have not seen his designs, or haven't seen very many of them, and we don't really understand how they were made. So we've been working with the Huffman family. They were just visiting MIT last week to reconstruct his way of thinking, how he was able to design these patterns, and in particular, reconstructing his designs. So these are sort of reverse engineered crease patterns. This one folds into this. Not very obvious. This is one of the more surprising ones. And then this is our folding of his design, just to check that we got it right. I don't have here a photo of his folding, but they look the same. That's the idea. So this has been really exciting, and he has over 150 designs, and been learning a lot about how he was able to design with curved creases. Most origami uses straight creases, which is relatively easy. Okay, back on the sculpture side, we wanted to combine glass blowing with paper folding. This is my dad blowing glass blindfold. Don't try this at home. And so this is at least 1800 degrees Fahrenheit. He's touching it through a pad of newspaper, which protects him through a layer of steam, and a little tricky to find where things are. And that's his only interaction with the piece. The goal was to make glass blowing more like paper folding. And with paper folding, it's all about the tactile experience. It's all about feeling that piece of paper and reacting to that. So we wanted to recreate the same thing with glass, so we could combine them together. And I haven't tried this. I'm not quite as crazy as my dad. But I'm told, it makes you much more sensitive to the feeling of glass and these shapes. So that's a completed, we call them glass heads. He didn't burn himself, luckily. We made a lot of those glass heads, and then you've seen this, how to fold a circle of paper. You should try this at home if you have a compass. It's pretty cool. It takes a while, but once you've folded this, you can squeeze it really tightly and put it inside the glass head. So here it's been wound up really tight. Kind of squeeze it in like a ship in a bottle, push it around in there, and then you've got your shape. And this is really cool because the glass enclosure adds another constraint on how that piece of paper can unfold, and it forces it to stay tightly folded. So you get a very different set of foldings out of that combination. We've been playing also with putting pieces of paper on the outside of glass. And there you get these really cool optical effects because glass acts as a lens different places. So it's probably hard to see, but you've got paper on the outside here. It goes through a hole there and then weaves around, and then there's another hole that goes through back there. And I think there's a lot more potential. I've shown you glass folding, but even with sort of traditional glass blowing, you can combine it with paper folding in really interesting ways. So that was our little tour of pleat folding from art to math to 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 art. And it's been a lot of fun to go back and forth. There's still a lot of challenges both on the art and the math side. And they really inspire each other and make us do more interesting artwork and more interesting math work. I want to show you just a few more examples. One idea is getting back to this, a sheet of material that could fold itself, that has no origamist involved. I would like to just unroll my sheet, connect my battery, and boom, I get an origami table without the origamist involved. So these are examples of robots we built that are, the robot is the sheet of material, not paper. But the vision is, I want to build a transforming robot that can change its shape from one thing to another. And ideally, this gadget, I push a button, it unfolds, and then refolds into a chair so I can sit down. I'm getting tired up here. And then I unfold and refold into a couch so I can get my volunteers up here. Whatever gadget I want, I should be able to make by folding. And so we needed a way, one crease pattern that could fold into many different things. And we came up with this grid. It's actually a traditional idea in origami called box pleating, where you fold a square grid with alternating diagonals. And origamists have used it to make many different things, but surprisingly, no one had proved that you can make anything out of it. So if you have any 3D surface you want to build, you can approximate it by little cubes. In the same way that we pixelize an image, you can voxelize a 3D solid. And then this sheet, if you have enough grid lines, will fold into any combination of cubes, any structure made out of little cubes. And so if you can build a robot like this with a sufficiently fine grid, you can make any 3D shape, then unfold, then make any other 3D shape, and everything is possible. Now, to make something like this, you need a fairly large grid. This is probably 64 by 64 or so. So far, we have built 4 by 4 grids. So the theory is way ahead of the practice in this case. But here's our coolest example. This is one sheet. If you send it one signal over here, some electricity, it will fold into an origami boat. And there are some magnets to hold it closed once it's fully folded, which is now. And now you can release the electricity and it will stay in this state because of the magnets, fairly small. Or you can send it a second signal. And there are little, kind of like muscles here. They're called shape memory alloy. They're essentially little strings. And when you heat them up through electricity, they coil up and pull the crease shut. And these are the next series of folds. And here you've made a paper airplane out of the exact same sheet of the same robot. This does not fly, I don't think. But the boat might float. So that is origami robots. Now, in the similar vein, they use the similar kinds of crease patterns. There's a particularly fun set of foldings you can do where you're folding a kind of maze. So this is folded from one square of paper. This is the crease pattern here. And essentially, you have little vertical walls coming out of your piece of paper, or coming out of the square once you've folded it. And this is also originally motivated by an art project, which I won't get into. The end result is we can prove you can make any maze you want. And if you want to play with this software, it is available online. And here it is. So you can start with, say, a random maze. And this is the 3D surface you will get if you fold this crease pattern. Don't try this at home. I would suggest something like a little smaller might be nice. You can customize your maze to be exactly what you want. There's like a letter E for my name. You fold this flat, which this would be pretty reasonable to fold, and you'll get exactly this 3D structure. Or you can write your favorite message here, like NYUAD. And get that right? Yeah. Then you fold this crease pattern flat, or not flat. You will get this 3D structure. So pretty cool, as like you can make anything. But we thought it would be fun to also bring this back to the art world. And so we designed, here's an example of an actual folded one from a sheet of paper, regular printer paper. So we designed a series of art prints that are kind of conceptual. They have on the top a crease pattern. It doesn't look like very much. It also has some gray regions here. Those are not creases, those are just patterns. And then when you fold this, you simultaneously get a 3D structure, which here is the word yes. And then in the background, the shadow comes together and you get the word no. Kind of a fun contradiction. And this is actually foldable. Some students of ours have folded this. But it's kind of fun just as a conceptual thing that this is possible. One that will never be folded, I hope, is this really complicated design. Again, we have a crease pattern with some dark regions here. When you fold it, in theory, you will get the word science in 3 dimensions, and you'll get the word art hiding in the background there. So this is a fun sort of series of using our mathematical results to design art. If you want to learn more about the science and art of origami, there's this cool movie you should check out called Between the Folds. It's an hour-long documentary, and it talks about a lot of people in the community on the art side and the science side and people trying to bridge the two. So a lot of fun. If you want to see the more mathematical side of how folding works, not just for paper folding, but also things like robotic arm folding, protein folding, and things like that, we wrote this book, Joe O'Rourke and I, on geometric folding algorithms. So you can check that out at your local bookstore or library. And there's also, if you're more visually inclined or you like hearing lectures like this, there's a whole series of video lectures, about 23 of them. By now, actually more like 50 of them. It's a little crazy. Of this class I teach at MIT, on basically the same as that textbook. And all of these videos are available for free online, so you can watch them, pick out the ones that sound interesting, try them out. Not too much math background required. If you want to see more depth than what I'm covering here, this is, for example, folding lots of little cubes to make an MIT logo. Then you can check that out. Just go to my webpage to see it. I wanted to show one more topic, which is a different kind of folding, just to give you a sense of other things that are possible, not just folding a sheet. Here we're folding a chain of blocks. And on the one hand, we get an equilateral triangle. And on the other hand, it folds into a regular square. This is great if people actually build tables like this so that if you have 2 guests, you can have the triangular table. If you have 3 guests, you can fold the square table. Just rearrange the parts. And this idea goes back to 1902. So it's very old. It's called hinge dissection. And we wanted to figure out, can you do this for any 2 polygons of the same area, any 2 shapes? So initially, we proved that if you have shapes that are made out of very simple structures, these right isosceles triangles, then you can do it. And to illustrate that mathematical result, we designed a font that had the property that this chain of 128 pieces can fold into any letter of the alphabet and any number, and it can fold into a square. So you could take the letter O, unfold, refold into the letter R, and so on. So it's kind of fun. Then we generalized it in 3 dimensions. This is kind of fun. An artist, Lori Palmer, was visiting Harvard, and she said, I've got all these blocks and all these hinges. I want it to be able to refold into lots of different things. We said, great, we just proved a theorem about that. And so we built it. This is about 1,000 blocks. It's an interactive sculpture. You pick up the gloves and start folding it into different shapes. And in theory, you can fold it into anything you want. Made out of cubes, of course. And then finally, a few years ago, we proved that anything is possible, not just shapes made out of cubes and cube-like things, but any polygons, as long as they have the same area. And I'm showing here 2 dimensions, but you can do this in 3 dimensions as well. Then you can make one chain of blocks that folds into a butterfly and then refolds into an angelfish and so on. And lately, we've been applying that to build robots. So I've talked about transforming robots based on folding sheets, but these are transforming robots based on folding essentially chains of blocks. So there's motors in here that rotate. This thing is quite large. It's taller than a human. And it can fold theoretically into any shape made out of little bricks in some sense. A little bit slow, but eventually we imagine transformers more than meets the eye that we can use to build my vision of making a gadget that can refold into any shape you want, or making a house that can change its shape dynamically according to, I don't know, the weather or how you're feeling that day, or whether you need a kitchen right now or you'd rather have a bedroom so all your furniture could just reconfigure and still have a very small space. I mean, anything is possible in theory, and we want to make that a reality. I hope you've enjoyed this little tour of the art and science of folding. Thanks.
Hi, thanks very much for the lecture. Very enjoyable. I was wondering how you created the computer programs, like the one that we saw earlier on your website.
Yep.
Is that I assume is based on the mathematics, right?
Yes.
But how did you create it?
So this computer program is implementing a rather simple algorithm that we first came up with theoretically. We proved that it worked. And we used it by hand to make things. And then we thought, oh, it'd be really fun if we had a computer program to do it all for us. That is sort of what we prove is possible. Then we actually make it happen. This algorithm is based on a simple idea, which is you look at each of the corners here. Here we have a corner that has a line to the right and a line to the left. And this portion of the crease pattern is the way that you make a kind of L shape up there. This is also an L shape. So this pattern, this little chunk here is exactly this, but rotated 90 degrees. And you just do that for, here you've got just one thing coming together, here you've got three things coming together in a T shape, and you make the corresponding pattern for each of those. These we designed by hand, but we did it in such a way that mathematically they're guaranteed to fit together. And then the computer program just fits them together. So, and we haven't done this for all of our algorithms, but they could be done. Each of the algorithms has different levels of complexity. They use different ideas. But it's just taking the ideas that are in our head and written in our papers and then running them on a computer.
I was wondering if you'd thought about taking some of the algorithms that you've taken and putting it into other mediums, like glass, for example.
OK. Folding something like this out of glass, I'm pretty sure is impossible. We're still trying to figure out the limits of glass folding and exactly what's possible, what's not. Glass folding glass is relatively happy to fold along maybe 2 or 3 lines at a time, but not much more. And when you fold this out of paper, you need to fold everything simultaneously. It's quite challenging, even with paper. Glass, on the other hand, is happier. It can stretch a little bit. It can shear a little bit. So I think glass can also do some things that paper can't. Paper can do some things that glass can't. So glass in particular, we're still figuring out where those boundaries are. It's a little early to say. But definitely we were inspired to try different algorithmic things. We started much simpler than this and try to apply them to glass. Sheet metal has been one of our other main areas of playing around. And I don't think we have a great way yet to make anything out of sheet metal. There are lots of issues with using the laser cutter, like I showed. But it's getting there. And sheet metal is pretty compatible with at least relatively simple folding designs. I mean, that bunny was not so simple. This might be a little harder. Some plastics you can also fold, like polypropylene. Some people have been very successful with. We haven't tried that personally too much. What else? In general, any sheet material that has good elasticity, that remembers what you tell it. When you crease it, it stays creased there. It should work well. But of course, every material is a little bit different. One material that works really poorly is rubber, sheet rubber. Because you fold it, and then it remembers its original state. You cannot change its memory. It just unfolds every time.
Hi. Thank you for making something so complicated, so accessible for all of us. One of my mentors, Dr. Patsy Wong Iverson, has always tried to encourage me to incorporate origami with mathematics. I'm trying to get an idea of how to do that with my children. What is an area in the curriculum that you would start with beginning origami with mathematics for children?
OK, good question. I'm not the best person to ask this question, but you might start by watching Between the Folds, because there's a segment in there about a whole schooling system in Israel built around the using origami to teach geometry. Basic principles like angles and edge and segments and angular bisectors. There's a lot of basic geometry, Euclidean geometry, if you remember that stuff from high school or whatever, that you can just see physically on a piece of paper. And that's been really successful. I haven't been directly involved in that, but it sounds really cool. And yeah, so that's the starting point. I don't know, how old are your kids? I can't quite see. 10. Well, so at this point, they should be doing advanced mathematics research. So then they can read our book. Yeah, so it depends. I think, so there, I mean, you can do sort of classic, understood mathematics, but then very quickly you get with origami into areas that no one knows the answer to. Like how to refold a roadmap other than differently is still unsolved as a mathematical problem. There are tons of things. I think that's really exciting for kids and adults because I've showed you lots of things that are true, but there are tons of things we don't know whether they're true or false, or we just don't know what the answers are. And that's in some ways even more exciting. So I would try to go there as quickly as possible, not necessarily to solve those problems, but to show the limits of what we know. I think that's really appealing to kids when adults don't know things.
Hey, I was just wondering if you ever applied the structural aspect of it to be load-bearing. For example, you showed a robotic model of a table.
Right.
Does it actually distribute the load equally amongst the pillars or the columns?
That's a good question. So can you make these foldings load-bearing? This is not my expertise. Most of our mathematical models ignore structural properties. But some of my colleagues are investigating that. And I think this should be possible. And in general, folding sheets make them stronger. I mean, like corrugated cardboard is a classic example. When you fold, you get a stronger material than just the bulk material as a sheet. And so that's exciting. And we need to do is adapt that kind of structural analysis into these kinds of algorithms. And that hasn't been done yet. So then you can make really complicated surfaces that are still load-bearing. So that's something that needs to be done.
A very interesting lecture. I would like to ask a more mathematical question. Like you've shown us that you can refold any 2D shape in any other 2D shape and any 3D shape into any other 3D shape. Does that work in general n dimensions as well?
Good question. So I remember. So in 4 dimensions, I think. So it depends exactly what you're asking about. If you're asking about these foldings, the hinge dissections, you need not only the volumes to match, but there's another weird property called the Den invariant that needs to match. And that is also all you need in 4 dimensions. And I believe in 5 dimensions and higher, no one knows the answer. But what we prove is that if you can take any shape in any dimension and cut it into pieces and then just like pull them apart and rearrange them into some other 3D shape, then we can do that with hinges. So we can turn it's called a dissection, where you just cut it into pieces, completely rearrange them. We can turn that into a folding structure. So whenever it's possible without folding, we prove it's possible with folding. That's the short answer. And that works in any dimension.
Totally fascinating. And I wonder if you are working with any architects that are taking this to a larger scale.
Yeah, definitely talking to a lot of architects at MIT and happy to collaborate with more people here. I know there's a lot of great architects working in the UAE. And so, for example, there's a bunch of architects taking my class. This is what the class webpage looks like this semester. And I think that's really exciting. There's a lot of design potential in general. And then specifically, I would love to make buildings that actually reconfigure. Chuck Hoberman Associates, is one of the leading people taking folding ideas and applying it to architectural scenarios, but I think it's just scratching the surface. There's a lot more possible.
So on one hand, you have this vision of a very exciting vision of like self-reconfiguring furniture and a house that refits itself, whatever. On the other hand, you've mentioned some results about being able to construct any arbitrary shape. So it sounds like everything's figured out, right? So what's missing? So what are the challenges before we get to this self?
So what's the discrepancy between theory and practice, essentially? There are a lot. There was the structural issues that you were talking about. which we're not modeling mathematically, and you need to when you build a real thing. Does it support its own weight? Can it support load? Things like that. Another big challenge is thickness in material. Paper is pretty thin, and so when you're folding paper, you can get away with modeling paper as essentially zero thickness, and that's what we do in all of our mathematics. But when you're using thicker materials and more structural materials like sheet metal, things get a lot thicker. The same issue arises with robotics. And we need a way to model that mathematically and design origami that works even with very thick material. There's been some progress on that recently, but it's still kind of in its infancy. Those are the two main challenges, I think.
Have you been looking into applying this at the molecular level? I mean, extending from the architectural level. What about the other extreme?
Yeah, I think
like protein folding, for example, or those kinds of things.
Yeah, so there are multiple molecular levels. One that I'm interested in both protein folding, which is proteins are the building block of life. They make up every living creature that we know. They're essentially one-dimensional pieces of paper, and once they're created from your DNA, you all know DNA is important from Jurassic Park, and then the proteins fold into some shape which determines what it does. How does that folding happen? We don't really know. And we're trying to take the kind of computational origami understanding we have for how to design 2D sheet folding structures to the 1D folding, which should be easier, right? But it's not so easy. The idea is to take that mathematics to inspire conjectures on what might be happening biologically. If we were designing nature, for example, designing proteins, how would we make them fold? And that will hopefully lead to interesting hypotheses for biologists to prove. A little bit bigger, like more the micron scale, I think making things at nano and micron scale is really exciting for application for folding because we have really good ways to make 2D patterned sheets. We do it all the time with chips in our computers. Lithography, make like a stencil and then shine a light. And you can get really complicated, super high resolution detail in a wafer. If you could then get that wafer to fold into 3D structures, then you could make super high resolution 3D structures. So that's something we're exploring.
You mentioned one of your earlier projects was with the glass and the color inside, and you said it was meant to be a sort of puzzle to figure out. Could you tell me how you did that?
Oh, well, we're on video. I don't know. Okay, I'll tell you. So the basic idea is if you have a glass bubble and you poke some glass, like you take a metal tool, you poke on the side, you'll get a indentation. You do that on both sides, you can get the two indentations to meet. And glass is extremely sticky, so once it sticks, it will stay stuck unless you get it super, super thin. So the idea is you have a nice round bubble, you completely destroy that bubble by poking lots of pointy parts into the center, get them to connect. And once they connect, they'll stay connected, and then you fix the shape of the bubble. That's something, it's easy for a glass blower to do. You make it nice and round again, you blow it out, and so on. And what's cool is when you do that, you preserve all those connections on the inside. And it's a challenge to make them not fall over and hit the walls. And it takes finesse to do this in a cool-looking way, but that's the basic principle. And that takes a little while to figure out because you're not used to completely destroying your outer structure in order to make connections on the inside and then fixing it later.
Actually, that question is from my son. He wanted to ask about the mathematical representation of the efficient folding for n creases represented by 2 to the power square root of n, was it?
Oh, yeah. Oh, so the dragon curve thing? Yeah.
He's asking how can 2 to the power of square root of n represent number of creases that can be irregular?
Oh, well, so there's two answers. There's the 2 to the n, which is if you just fold in half, fold in half, fold in half. And that's not too hard to figure out. I was actually just teaching this last week, so hopefully I can still do it. When you fold, I'm going to write M for mountain, V for valley. After you make 2 folds, it looks something like this, because you fold it in half here first. And then when you make a mountain fold, say here, This one's upside down, so it looks. Can I draw this? Valley, mountain, mountain. That's after you fold it twice. After you fold it a third time, you'd get something like this. I'm just reflecting and complementing over here. After you fold it a fourth time, you get this. Sorry, red on red. It's easy to see, huh? Let's see, valley, mountain. If you look up dragon curve fractal on Wikipedia, it'll explain this recurrence. And so it's a really weird pattern of mountains and valleys. Fairly easy to generate computationally, but not what we're looking for in mountains with alternating MV, MV, MV. If you want to know the 2 to the square root event solution that does it nice and regularly, you should watch the lecture. That takes 10 or 20 minutes to explain. All right. I think that's all we have time for. Thanks, everybody, for coming out. Hope you had fun.